It is on the formulations of issues and constraints for our project using the Unified Modeling Language, which stands for UML, which stands for Unified Modeling Language. And again, this is part of our discussion on the concept definition for our system. And there's a lot of information about this unified modeling language online, and there are books about it. I have listed 3 references here, which might be useful if you have questions. But in general, what we're going to be discussing in this lecture is enough for what you need to accomplish for your project. So Unified Modeling Language is a language for visualizing, specifying, constructing, and documenting the artifacts of software-intensive systems. So this was the initial purpose of this language, was focused on developing software-intensive systems. But in the past, I would say 10 years, it's also, people have found that it's useful also to describe other type of systems, like the ones that we are discussing in class. So it is not just something that is used for software development, it's also applicable to the description of any type of system. So this is a standardized specification language for object modeling. This is something that was developed, and I think right now IBM is the one that owns this language. A general purpose modeling language with graphical notation used to create an abstract model of a system. So the idea is that you can start putting together some of your concepts for your system. And there are different diagrams that you can use for different purposes. UML is officially defined by the Object Management Group. And what are the things in the UML? Structural things. These are mostly static parts of a model. Structural things are called classifiers. Those could be classes, interfaces, collaborations, use case, which we defined in our previous lecture, active class, components, artifact, nodes. We're going to discuss them today. And behavioral things, such as dynamic parts of UML models that shows interactions, state machines, or activities that can happen in your system. Grouping things also, as you saw in doing this semester, we always talk about the hierarchy structure of our system. So we start with the parts, and when we go up to the system level. So at some point we're going to start grouping things, and those can be subsystems of your system. So the UML modeling language also provides you with some diagrams that can be used to define those groups or those subsystems. Package, commenting things, these can also be very helpful if you need to explain something or make a note saying that this is what this is trying to represent. So there are also tools that we can use for that. Relationships in the UML diagram. Relationships are represented by the use of arrows. So here are 3 of them. This dotted line with the arrow at the end, the simple line, and this arrow with the white head. They're all used to, they're different in some sense. A dependency is defined by a relationship between 2 things in which a change to one thing, the independent thing, might affect the other thing. And that's represented by that dotted arrow. An association is just a structural relationship that describes a set of links. So something like, well, this chair will go with this table. Those is an association. And then generalization, a relationship in which the specialized element, the child, builds on the specification of a generalized element. So this is something like if you're building a system that can be used for many things, like for example, you're using GPS technology A GPS can be used for set up driving routes, but can also be used to identify where people are located. So in general, the technology is the same, but when you start defining that relationship, that generalization, you have the GPS system at the top, and then the child will become the applications that are born from that technology. And I'm going to show you some examples. So there's 13 different types of diagrams in UML. The following pictures provide a way to characterize them or categorize them in a hierarchy. So the diagrams, there's at the top level, and there's structure diagrams and behavior diagrams. So you see there's 13 of them. We're going to focus on those that are highlighted in red. So from the structure diagram, we're going to focus on the class diagrams. So structural in the sense that you can define what are the parts of your system. So we're going to use the class diagram to show those. So we can see, so if I have a system that is a car, the class diagram at the top level is the car, but then we're going to have a class saying that we're going to have some wheels, we're going to have some exhaust system, we're going to have also I don't know, the engine is going to be another class, and so on. And then for the behavior diagram, we're going to discuss these four: the activity diagram, the use case diagram, state machine diagrams, and the sequence diagram. And those were introduced in our previous lecture. Today we're going to review them one more time. So use case diagram, this describes the functional behavior of the system as seen by the user. So if you're the user, how do you see this thing working? Class diagram describes the static structure of the system. So this is the actual system in terms of parts, in terms of components. Sequence diagrams describe the dynamic behavior between actors and the systems, or the system, and between the objects of the system. A state chart diagram, this looks like one of the diagrams, the causal loop diagrams that we discussed in class is very similar to that one. Describe the dynamic behavior of an individual object as a finite state machine. So we're going to have some states, and we're going to connect those states according to what's going on with your system. Activity diagrams model the dynamic behavior of a system, in particular the workflow. This is very similar to a flowchart. So if you're familiar with flowchart, it's the same thing. You're going to have the diamonds representing decisions, rectangles representing the operations, and so on. So let's start with the behavior diagrams. And we're going to start with the use case diagrams. So a use case is a model of the system functionality. It is a description of the functionality of the system and its environment. And it's used during the requirement elicitation, discovering the requirements to represent the external behavior. So at some point, we talk about how use case will be linked to the description of your requirements. These are diagrams that are very easy for the user to understand, very simple to create. So you're going to have these three things, or two things actually. These two are representing the same thing, the actors and the use case. And we're going to use those to describe the behavior. So two main components of a use case are the use cases and the actors. Actors represent roles, that is, the type of users of the system. So we talk about the example of the HVAC system in which you have the AC, you have the heater, and how the actors work interacting with the operations of these two main things. Use cases represent a sequence of interactions for a type of functionality. And the actors are the ones who triggers the use cases. So again, actors represent an external entity which communicate with the system. So it could be, it doesn't have to be a physical person. It could be a material thing, such as the HVAC, like we discussed before, like you have the heater and the AC, those can be actors. An actor has a unique name and an optional description. For example, we can have an actor representing a passenger. A GPS satellite can be also an actor, which provides a system for GPS coordinates. The use case. A use case represents a class of functionality provided by the system as an event flow. Think of main functions a system performs for users, like cases of using a system. For example, if you look at the cell phone, you have the following functions: place a phone call, receive a phone call, use the scheduler or the calendar. Each actor must be linked to a use case, while in some cases, some use case may not be linked to the actors. So all your actors has to be linked to one of the use cases in your diagram. But the use cases not every use case has to be linked to all the actors. So here's a description or an example of a use case for the cell phone. So those are the three functions that we listed for the cell phone, right? The place phone call, receive phone call, and use a scheduler or the calendar. And you see in our case, we have two actors. One of them is the user, which is the person using the cell phone. And on the other side, we have the cellular network, which is we can think about it as an antenna. So how is these two actors interacting with the use case? Again, this is used to represent some of the behaviors of your system. And also, if you go and develop these diagrams, you can start identifying some of the parts that might not be part of your description yet. So in this case, you think about, okay, I'm going to have this system, I'm going to be dealing with a cell phone. So what are the things that I need to take into account when I'm dealing with a system that requires the use of the cell phone? Well, the user is going to be very important, but also the system that is helping me make the cell phone function. In this case, the cellular network. So what are the interactions with those? Are those relevant for my system? So in this case, for me to be able to play the phone call, which is that action at the top, I need to contact the cellular network. The cellular network is going to call that person that I'm dialing. And then if the person connects, then I'm going to be able to receive a phone call. The other way around, the person contacts me, cellular network is going to put a notification in my device, then I'm going to be able to receive that phone call. In terms of the use of the scheduler, you see there's no need for me to connect with the cellular network. That is an application in your cell phone. There's no need, that will work even if your cell phone is not connected to a service provider. So that's why we have this type of connection here. We don't need to have a direction defining that interaction. So another diagram here, I think we discussed this one earlier in the previous lecture. This one is representing the interaction between a user, let's say a student, and the library. So what are the things that you can do in the library? These are listed here. So how is the member connecting with those? Are those one-way directions or two-way directions? And then who is also interacting with these actions? So in this case, the circulation clerk and the supplier. So it's the same idea. You see, you're showing up some of the actions that your system is going to perform, and that's helping you visualize who are or what are the entities interacting with those actions, identify those as part of your system, and then also, if you have not considered some of them, those are going to show up as you bring more detail into these diagrams. Another example, so use case diagrams extend relationship, linking an optional use case to a standard use case. So for example, registered course, that will be the standard use case, may have registered for a special class, which is an extend use case. The optional use case extend the standard use case. Standard use case can execute without the extend use case. So that's where we are showing up in this diagram. So you have some type of hierarchy here in this action in which you are registering for classes, but also there might be some external or additional actions that might not happen to everybody. Let's say you're a student that is on probation, so you might need to go and register for, or you're admitted with some restrictions, so you need to register to special courses in order to start your courses or general courses as part of the university. So those are the things that are represented here, the extended use cases. So it's registered for a special class. So right now we have our students starting with Calculus 1. So if you are not, if you don't have the requirements to start with that class, you're going to have to take some previous or pre-requirements to be able to take Calculus 1. So that's basically registering for special class. And then identifying prerequisites for courses not completed. That could be another extension. And this is the example that I was referring to, the HVAC system. So we have all the actions of the system, and then the actors, which are the homeowner and the heater and the AC. So you see these diagrams they look different in terms of the colors and how the actors are represented, but the idea is the same. The difference is because they're built using different software. There's software that we can use to build these diagrams, and I'm going to show you an option at the end of this lecture. So any questions about use cases? Let's talk about class diagrams. So class diagrams, as I mentioned at the beginning of the lecture, they're structured diagrams. So the idea comes from software development. So we're going to have a type, an abstraction in the context of programming languages. So what type of entity are you trying to represent? Like, for example, we can have an entity that is called an integer. Purpose is to represent an integer number, and the members of that class will start with a 0, and then will continue. An instance is a member of a specific type. The type of a variable represents all possible instances that the variable can take. So, the instance is coming from the type. Class is an abstraction in the context of object-oriented languages, encapsulate both state, variables, and behavior methods. So here's a class diagram. Okay, so here we have a class diagram that is representing a bank account. So the class diagram, or the way that you represent a class, is with this box. At the top, you're going to have a name for the class, and then in the middle box, you're going to have the attributes, meaning that these are the characteristics of this class. And then operations basically are the functions that class can perform. So if you're looking at the GPS system, the name will be the GPS system. The attributes can be, well, we can manage this many nodes, or we have a radius of this length. And the operations can be, okay, we can perform these type of analysis with the GPS system. So a class is an abstraction of a concept within a computer program. Again, this is based on the concept of defining a software. A class encapsulates state, attributes, and behavior operations. The class name is the only mandatory information. So if you're defining your classes, the only mandatory or needed required information is the name. All the other information will be additional. There are also relationships in class diagrams. So for example, there's an association in this case, in which we have a flight and a frequent flyer information. So, so the flyer information can be linked to that frequent flyer account. So these associations denote some type of relationship between the classes, represent the ability of one instance to send a message to another instance. There's also the concept of multiplicity, which is going to represent, so one of these can represent many of this, or one of these can represent many of this. So these are the ideas represented in this table. So we have an indicator, which is what you see here. So this represents 0 or more, and 0 or more. You can have 0 or more flights, or you can have 0 or more frequent flights in every flight. So that's what this is representing. But also you can have 0 or 1, or binary. You can have only 1. You can have 1 or more n, where n is greater than 1, 0 to n, and 1 to n. So here's an example of a 1-1 association. So you have a country, and then every country will have one capital. So that association is 1-1. If you have a polygon might have many or has many points. So it's a 1n association. So that's what this is trying to represent. So if you see those numbers, that's what this is trying to represent, those multiplicity. Aggregation, this is important for your description. So this is ideally what you're going to do to represent the components of your subsystem or your system. So this diamond here, this line with a diamond at the top, what that represents is that you have parts that together create this at the top. So the exhaust system will have a muffler and a tailpipe. Okay, so this is what this aggregation is representing, the components of that top class. A special case of association denoting a consists of hierarchy. The aggregate is the parent class, the components are the children class. In UML, it is graphically represented as a clear diagram shape on the containing class N. Okay, so here's a generalization. It's a different type of relationship. So this is to represent a hierarchy. This one is to represent a generalization of your top class. So meaning, like, if you are thinking about animals, you can think about the different group of animals. So at the top you can have mammals, and then a generalization of all the animals that will come at the bottom. So you can say mammals here, and then you can have all the animals that are represented as part of that group. Okay, so that's what this is representing, the generalization. I think I have an example. So the children classes inherit the attributes and operations of the parent class. Generalization simplifies the model by eliminating redundancy. So you don't have to represent every single thing every time. So the UML graphical representation of a generalization is a hollow triangle shape. Class diagrams represent the structure of the system. As I mentioned already, class diagrams are used during the requirement analysis to model the problem domain concept, during the system design to model the subsystems and interfaces, and during the object design to model classes. So here's a good example of a generalization. So you have a bank account, and the bank account has these attributes and these functions. When you generalize that, you can have a checking account and a savings account. The checking account will also have these two attributes and also these functions because it's coming from the parent. So you don't have to duplicate this information here. The only thing you have to do for the checking account is include the functions and the attributes that are not part of this one. Same thing here. These attributes and functions will come as part of this one. The only thing you have to specify here are the functions and the attributes that are not part of this one, of this class. So it saves you duplication. You don't have to duplicate everything. You just start with the top level, the general class. You list all the things that are common for all the classes that are going to come after that, and then you start splitting those that are different. So here's another example. So this is a diagram, a class diagram representing a company. So here we have an aggregation. So again, these are elements of the company. So within, at the top level, we have the company. These are subsystems. You can see that the departments, and you have the offices. So within the departments, you have some relationship here, which are the people who are working as part of the department. And then in office, you have a generalization here in terms of what type of offices you're referring to. So you have the headquarters, those are a different type of offices. And this is a very nice example to show all the things that we just discussed. Okay, so the use of those arrows, and those are highlighted here. Another example, this is the class diagram for the HVAC system. So you have also as part of the class diagram, you can include those actors as we did for the use case. So you have the controller. The controller is going to have an association with the AC interface, the heater interface, the thermostat. So in this case, there is no generalization or aggregation. But you see how can you build the entities of your system and how they're connected. So this is the structure of your system. Questions about class diagrams? Okay, so sequence diagrams. This is a, so again, for the purpose of this class, in terms of structure diagrams, we're only going to focus on the class diagrams. The rest of the diagrams are going to be behavior, including the use case diagrams. So the sequence diagrams are next. Sequence diagrams represent the behavior in terms of interactions between the systems entities. Complement the class diagrams, which represent the structure. And it's useful to find participating objects. These are time-consuming to build, but they're worth the investment. Again, allows you to identify things that maybe you haven't considered. And also can be used to creating system test scenarios. So in a sequence diagram is an interaction diagram that emphasizes the time ordering of messages. Graphically, it's a 2D table that shows objects arranged along the x-axis and messages ordered in increasing times along the y-axis. So time is going to be represented by the line going from the top to the bottom. And then you're going to have your objects at the top. And you'll see as time progresses how those messages are shared between objects. So if you have your class diagram, you can just pull those objects and put them at the top, and then you start seeing how messages are transferred from object to object. So here's an example. You have a ticket machine and a passenger. So as time progresses, let's say this you're building a ticket or buying a ticket for a subway or a train. So you select the zone where you want to go, you insert the coins, pick up change, pick up the ticket, and then go. Okay, so the interaction is between the passenger and the ticket machine. Sequence diagrams are used during the requirement analysis to refine the use case description to find additional objects, and also is used during the system design to refine the subsystem interfaces. Classes are represented by columns. So again, those classes are listed at the top. Messages are represented by arrows. And these activations are represented by narrow rectangles. So these bars here are representing time. This is the time that it takes to complete this action. This is the time it takes to complete this action, and so on. This bar right here is complete because this is the complete time spent by the passenger. Another example, so let's say you're trying to set up your watch time. So this is what's going on here. Watch user is at the top. They have the watch, they have the LCD display and the time. So as you start the action, just press the bottom, blink hours, then press the bottom, blink minutes, press the bottom, blink increment the minutes, refresh, go back, you're done. So again, time consuming, but gives you a very good idea of what's going on or what needs to happen in your system. Another example, let's say this is a web interface for teachers to log in, something like Tracks. So the teacher will log in, web interface will validate the user, database will return that message, and then you can log in into the system, retrieve information about students. So if I want to access some of your information after login, I can do that, and then you'll go through the same process. The HVAC system is, again, self-explanatory. You have at the top, you have the classes, and then how these classes interact with each other. Any questions about sequence diagrams? As part of your preparation for the project and also for the exam, you're gonna have a homework that is going to be open today, and it's gonna ask you to build some of these diagrams. Okay, so I just want you to be aware of that. State chart diagrams, again, very similar to what we discussed as causal loop models. So you're gonna have some states. In this case, they're not necessarily states; these are actions. And then those arrows are going to be linking the trigger for those actions. So your idle, this is representing the start of the actions of this circle. Your idle, the phone rings, wait for the answer, and then if you hang up or the caller hang up, then you go back to idle. If you answer the phone, then you're receiving the call. Until you hang up, then you go back to idle. If you're making a call, then you dial, making a call, hang up, you go back to idle. So again, it's representing the state of your system according to the actions that are performed. Okay, so it shows the life cycle of an object. It is a condition of an object for a particular time. An event causes the transition from one state to another state. And here's the state chart for a phone line object. Here's another example. This circle represents initialize. This circle is similar, but it has the white line around it, represents the termination. So you start with an open incident. This is a fire notification. So open incident, you notify the chief. This is the event triggering the action. Low priority, allocate resources. Not fire, and high priority, you notify the police chief. And if it's a fire and it's high priority, you notify the fire chief. And all of them are going to allocate resources, depending on the type of activity. And here's the state chart of the HVAC system, which has been one of the examples that we'll be discussing this morning. So again, very self-explanatory. Here's the heater. So you start the heater, you're off, the room temperature goes below its specified threshold, you're going to turn on the heater. That temperature goes below or above the upper threshold, you're going to turn off the heater. Activity diagrams, and I think this is the last diagram. So this is very similar to a flowchart. So if you're familiar with flowcharts, this is the same idea. An activity diagram shows flow control with a system. Activity diagram is a special case of a state chart diagram in which states are activities or functions. And here's the idea. So if you're familiar with flowcharts, diagrams or these diamonds, represent the decision points. So depending on the decision that you're making, you go one way or the other. And then these are activities or functions. Identify customer, make a reservation, check available space, reserve, and so on. So depending on the decisions that you're making, you go one way or the other until you confirm, in this case, the reservation for your customer. So activity diagrams there, those are simple. I know you're familiar with flowcharts, so this is the same idea. So in summary, UML provides a wide variety of notifications for representing many aspects of system development, are powerful but complex language, and is used in system modeling for model-based system design. So we describe some of the UML diagrams: behavior model, use case diagram, structure, object model, class diagram, and behavior model, sequence diagram, state chart, and activity diagram.